process scheduling. Here first we'll discuss about what are the basic concepts in process scheduling. Okay, we have seen, right, the single process system. What the single process system will do, will be having only one process that can run at a time. In single process system, only one process can run at a time, right? Okay. And if there are any other process, okay, those processes will be waiting in the waiting queue. Okay. In single processor system, there is only one processor to run the process. So if we have 10 processes, the in that any one can be executed by the processor here in single processor system. Okay, only one process can run at a time, and other process must wait until the CPU is free. Okay, other processes will be waiting until this processor is free. Other processes will be waiting in the single processor system. Okay, and after once the CPU is free, these other process will get rescheduled in single process system. Right? We have discussed this. Right? If it is a single processor system, at a time it can execute only single process in single processor system. Okay. Whereas in multi-programming environment, the objective of this multi-programming is to have some process running at all time by the CPU. Okay. Even though it is a single processor system, the processor will be executing all the time in multi-programming system. Okay, here multiple programs will be kept in the operating system. Right, whatever program we write, that program will be stored in the hard disk. Right? Okay, that will be stored in the hard disk. When if you want to run the program, that program will be from the hard disk, it will be transferred to the memory. Okay, from the memory, processes will be waiting for the processor to get allotted. Okay, if the process will get allotted, that process will get executed by the CPU. Okay, in multi-programming, there will be multiple processes will be running at the CPU will be running the process at all the time. Okay. Here the objective of multi-programming is to maximize the CPU utilization. Here in single processor system, which is running only one process at a time, the time if the process which the CPU is running, that the process, if the process needs to wait for some any IO device or something, the time the CPU also will be waiting idle until that process completes its IO operation and come back. Until that, the CPU will be waiting. Okay, it will be idle. Whereas in multi-programming, there will be multi-programming. Some process will be running all the time in the CPU, so that will maximize the CPU utilization. If one program the CPU is running, the time that program may get IO request, okay, that process may be eh, getting serviced by the IO request. By that time, the CPU will get allotted to another process in multi-programming environment. Okay, okay. With multi-programming, several processes are kept in the memory at one time. Okay, at one time there will be many processes will be kept in multi-programming. Okay, in single processor system, if it is a single process, only one process will be kept in the memory. Only that process will be executed by the CPU. Whereas in multi-programming, there will be several processes will be kept in the memory at one time. Okay, when one process has to wait for any IO request or something, the operating system takes the CPU away from that process. Okay, if the assume that a CPU is running a process one. Okay, that process one maybe needs to wait for some IO request. Okay, that time the operating system will take that CPU away from the process one and then gives the CPU to another process. Assume it like process 2, P2. Okay, this will be done in multi-programming. Okay, there will be several processes are kept in the memory at one time. When one process has to wait, the operating system takes the CPU away from that process and gives the CPU to another process. Understood this? Multi-programming. The CPU is one of the primary computer resource, right? The program will be, process will be executed by the CPU. What is process? Process is nothing but program under execution. We call it as process. Okay, that will be executed by the CPU. So it is the primary computer resource. Okay, and its scheduling is central to the operating system design. It is the important one. So the scheduling is also important to the operating system design. Here we'll be learning about process scheduling concepts. That is nothing but CPU scheduling concepts. Okay. Before going for that, we'll see the basic things which we will be using here is CPU IO burst cycle. Okay. Here, um, process execution consists of a cycle of CPU execution and IO wait. Okay, that together we call it as process. Process will be consist of CPU instructions as well as IO instructions. Okay, CPU burst or IO burst is nothing but it's the instructions. Okay, CPU instructions, set of IO instructions. A process consists of set of CPU instructions as well as set of IO instructions. Okay, it will process execution will be consist of cycle of CPU execution and cycle of IO wait. Okay, this is CPU or IO burst cycle is the process execution consists of cycle of CPU execution and IO. Okay, IO wait. Here the burst is nothing but CPU burst or IO burst is nothing but set of CPU instructions and set of IO instructions. And the process execution starts with the CPU burst. Always the process execution will starts with CPU burst and the process execution also ends with the CPU burst. Okay, process execution starts with CPU burst and this process execution CPU burst will be followed by a IO burst. Okay, process execution always starts with CPU instructions. After executing some set of CPU instructions, IO instructions will get executed. Okay, this is the process execution. Okay, process execution always starts with CPU burst and then that will be followed by IO burst. Okay, the final CPU burst ends the system request to terminate the execution. Okay, see, first always the process execution starts with CPU burst, that will be followed by IO burst. If there are any CPU other instructions, then CPU burst will get executed, then again IO burst will be executed. Like that the process will execution will continues, but the uh, last burst will be the CPU burst. Okay, the final CPU burst ends the system request to terminate the execution. Okay, last instructions in the process execution is CPU burst only. Okay, process execution starts with CPU burst and ends with CPU burst. In between we'll be having a CPU burst, IO burst, again CPU burst and IO burst. Okay, the duration of CPU burst will vary from process to process and from the computer to computer. We'll see with the diagram here. Yeah, this is alternating sequence of CPU and IO burst. Okay, the first we discussed, right? The always the process execution starts with CPU burst and that will be followed by a IO burst. Okay, you can see here CPU burst is nothing but set of CPU instructions like load, store, add, store, read from the file. Okay, these are the set of CPU instructions. When the control identifies the read from the file instruction. Okay, this is the read from the file instruction that specifies the process waiting for the IO operation, IO read operation. That time IO burst will get executed. Okay, here we once if it sees that read from the file, then it needs to read the content from the file. Okay, that is a IO operation. So we process will wait for the IO. Okay, then a set of IO burst will get executed. IO set of IO instructions will get executed. After that, again CPU process will resume with CPU burst. Here we have the store increment index write to the file. Once the control identifies this write to file instruction, this is a IO operation. Okay, then control will process will wait for IO. After execution of writing the content to the file, then again it will resume with CPU burst instructions. Then if there is any read from file instruction, again the process will wait for the IO instructions. Okay, then it will execute the IO instructions. Again it will execute the CPU instructions. Okay, ending instructions of the process is nothing but the CPU burst. Okay, CPU instructions will be executed at the end. Okay, understood, right? How the process execution will be. Process consists of set of CPU instructions and set of IO instructions. CPU instructions are nothing but CPU burst. IO instructions are nothing but IO burst. Okay, and these first always the process execution starts with CPU burst. Okay, that will be continued by IO burst. Then next will be having the CPU burst. Next will be having the IO burst. Okay, if you take an example as C program. Okay, C program always the program execution will start with main method. Okay, after main method we declare the variables, we allocate memory for the variables. Okay, uh, and then if you the control identifies the scan function. Okay, scanf or printf, that time the process will get the CPU will get become idle until the program gets the input from the user. Okay, until we give input to the program, the program will be waiting state. Okay, that is the program will be shifted from, by seeing the scanf statement, program will be shifted from CPU bus to IO bus. Okay, these are the printf statement, scanf statement in the C programming will be the IO burst. Okay, declaring the variables and all will be CPU burst. Okay, always the program's execution starts with the CPU burst and ends with the CPU burst only. But in between, we'll be having a cycle of CPU burst and IO burst, CPU burst and IO burst. Okay, like this, the process will get executed. Okay, next we'll see the CPU IO bound. Okay, what is IO bound? IO bound is nothing but IO bound program typically has many short CPU bursts. Okay, here IO bound will be consist of more of IO instructions. That means more IO bursts. Okay, that program is called IO bound program. Okay, IO bound program typically it has the many short CPU bursts, less number of CPU instructions, more number of IO instructions. If the process is IO bounded program, if the program is IO bounded program or IO bounded process, which will be having more of IO, IO bus. Okay, less of CPU bus. Whereas in CPU bounded program or process, that might have few long CPU bus. Okay, CPU bus program will consist of more CPU bus and less of IO bus. Okay, that is the difference between IO bus, IO bound program or CPU bound program. Okay, CPU bound program will have more CPU bus. Okay, IO bound program will have more IO bus and less CPU bus. Okay, in CPU bounded program will have more CPU bus and less IO bus. Okay, this distribution can be important in the selection of appropriate CPU scheduling algorithm. Okay, depends on a process will consist of both the CPU burst as well as IO burst. Okay, if the process is having more IO burst, what type of scheduling we need to take? And if the process is having more CPU burst, what type of scheduling algorithm we need to select? Okay, that is very important here. Selection of appropriate CPU scheduling algorithm. Okay, that will be depends on distribution of the IO bound and CPU bound. Okay, understood this? This is the histogram of CPU burst timings. Okay, if the frequency is more, the burst duration will be less. Next is CPU scheduler. This is the another concept here. CPU scheduler. Whenever the CPU becomes idle, the operating system must select one of the process in the ready queue to be executed. Right? When the CPU becomes idle, what the operating system will do? It will select any one process which is in ready queue. That is nothing but which is in memory. Okay, when the program will be kept in the memory, if the program is ready for the execution, okay, process is ready for the execution, then the process will be in the memory. Okay, that process will be allocated to the CPU by the operating system whenever CPU becomes idle. Okay, and this selection is carried out by short term scheduler, that is called CPU scheduler. Short term scheduler or CPU scheduler. Okay, and there will be multiple processes will be in the uh, memory. Okay, that will be operating system will select any one of the process from that memory for execution. Okay, that selection will be carried out by short term scheduler or CPU scheduler by using some scheduling algorithms that we'll discuss in this session. Okay, the scheduler selects a process from the processes in memory that are ready to execute and allocates the CPU to that process. Okay, what does a short term scheduler will do? It selects the process from the set of processes in the memory which are ready to execute. Okay, that means the processes are in ready queue. Okay, and from the ready queue processes, one process will be selected by the scheduler. Okay, and that process will be allocated to the CPU to that that process will be allocated to the CPU for execution. That will be done by scheduler. Okay, this is nothing but short term scheduler. Okay, the ready queue can be implemented as a FIFO. Okay, first in first out queue, or it can be ready queue can be implemented as a priority queue or a tree, or simply an unordered linked list also. A queue can be an unordered linked list also. Okay, but all the processes in the ready queue are lined up waiting for chance to run on the CPU. Okay, whatever processes will be in the CPU, all the process will be waiting for the CPU to get allotted. Okay, once the CPU is allotted to the process, then process can get execute. Okay, all the process which are waiting in the ready queue will be waiting for the CPU to get allotted to it, and that allotment will be done by the operating system by using short term scheduler. By that is nothing but CPU scheduler. Okay, and the records in the queues are process control blocks of the processes. Okay, whatever records will be placed in the queue is nothing but the process control blocks, PCBs of each processes. Okay, next topic is preemptive scheduling. Okay, preemptive scheduling. The CPU scheduling decisions may take place when the process is in any of these alternatives. Okay, the CPU scheduling may takes place under the following four circumstances. CPU decisions may takes place under these following four circumstances. In that, the first one is when a process switches from the running state to waiting state. Okay, the switching from process switching from running state to waiting state. Okay, that is the first circumstances. Okay, here like an example, if we say as a result of an IO request or a invocation of a wait for the termination of one of the child process. Okay, that time the process switches from running state to its waiting state. Okay, if any IO request comes, IO instruction for the IO request instruction comes, the process will switch from running state to waiting state. Okay, next one is switches from the running to ready state. Okay, when a process switches from the running state to ready state, like if we say an example, when an interrupt occurs, when the process CPU is running a process, that time if an interrupt occurs, process will switches from running state to again it will be switched back to the ready state. Okay, another circumstance is like switches from waiting to ready. Okay, when a process switches from the waiting state to ready state, for this if we say an example like at completion of an IO, once process is here, you can see here process switches from running to the waiting state. Why the process will usually switches from running to the waiting state? It will, if the process needs to complete some any IO operation. Once IO operation is done, again the process will switches from waiting state to ready state. Okay, this is an another circumstances. Okay, next is when process terminates. Okay, when the process completes also, this is also one of the circumstances where the CPU scheduling decisions may be takes place. Okay, CPU scheduling decisions will takes place when the process is in any of these four circumstances. Okay, scheduling under 1 and 4 is called as non-preemptive scheduling. Okay, when scheduling takes place only under the circumstances like 1 and 4, we say that scheduling scheme is called non-preemptive scheduling. Okay, that is 1 and 4 is what it is, process switches from running to the waiting state. Fourth one is process when a process terminates. This is a when a scheduling takes place only under these first circumstance and fourth circumstance, then we say that the scheduling schema is called non-preemptive, or which is also called as cooperative scheduling. Okay, otherwise we call it as preemptive scheduling. Okay, preemptive scheduling, understood, right? If it is under these and this circumstances, we call it as non-preemptive or cooperative scheduling. Okay, otherwise this is called as preemptive scheduling. Okay, under non-preemptive scheduling, we'll see what happens. Under non-preemptive scheduling, once the CPU has been allocated to the process keeps the CPU until it releases the CPU, either by terminating or by switching it to waiting state. Okay, any one of these two circumstances. Okay, once the CPU has been allocated to the process keeps the CPU until it releases the CPU, either by terminating the process or by switching it to waiting state. Okay, this is non-preemptive scheduling. Okay, in a scheduling algorithm is preemptive. If it is a preemptive scheduling means once a process has been given to CPU and it can be taken away from the process. Okay, process is given, process is alerted to the CPU, it can be taken away also in preemptive scheduling. Understood, right? Non-preemptive and preemptive scheduling. In non-preemptive scheduling, once CPU has been allocated to the process keeps the CPU until the process terminates or the process switches from the running state to the waiting state. That is non-preemptive scheduling. Next is preemptive scheduling. If once the process has been given to the CPU and it can be taken away in preemptive scheduling. Okay, that is the difference between preemptive and non-preemptive scheduling. Next concept here is dispatcher. Okay, dispatcher, it's an another component involved in the CPU scheduling function is called dispatcher. Okay, dispatcher module gives the control of the CPU to the process selected by the short-term scheduler. Okay, what's the work of dispatcher? Dispatcher module gives the control of CPU to the process selected by the short-term scheduler. Okay, this will involve the switching context, switching the user mode, jumping to the proper location in the user program to restart the program. This can be done by the dispatcher module. Dispatcher module gives control of CPU to the process selected by the short term scheduler. Okay, that is called dispatcher. And the dispatcher should be as fast as possible since it is invoked during the every process switch. Okay, every process switch is nothing but changing the process from one state to other state. That time every process switch dispatcher will get invoked. So the dispatcher should be very fast as possible. Okay, it should be as fast as possible since it is invoked during every process switch. Okay, next is dispatch latency. Dispatch latency means the time it takes for the dispatcher to stop one process and start another running is called dispatcher latency. Dispatcher latency is the time it takes for the dispatcher to stop one process and start another for running is called dispatcher latency. Okay, next is scheduling criteria. Next topic is scheduling criteria. Many criteria have been suggested for comparing CPU scheduling algorithms. Okay, these criteria are includes this CPU utilization, throughput, turnaround time, waiting time, response time. Okay, the first one is CPU utilization. Okay, CPU utilization is keep the CPU as busy as possible. That means the CPU must be kept as busy as possible. Okay, CPU utilization can be range from 0 to 100%. If it is CPU must be kept as busy as possible. And if the CPU utilization range is from 0 to 100%, in real time systems, it should range from 40% to 90%. Okay, if the 40% is will be for the lightly loaded system. CPU utilization 40% is for lightly loaded system. CPU utilization 90% is for heavily used system. Okay, next one is throughput. Throughput is number of processes that complete their execution per time unit. Okay, number of processes that complete their execution per time unit is called throughput. Okay, if the CPU is busy executing the processes, then work is being done, we say. Okay, work is done. The CPU is busy executing the process means we say it is work being done. Okay, the one measure of that work is nothing but the number of processes that are completed per time unit. Okay, number of process that completed their execution per time unit will be the measure of the work. Okay, this is called as throughput. Okay, for long processes this rate may be one process per hour. For the short process this throughput rate may be 10 processes per second. Okay, it is nothing but throughput is nothing but number of processes that complete their execution per time unit. Next one is turnaround time. Turnaround time is nothing but the amount of time to execute a particular process is called turnaround time. Here the uh, interval from the time of submission of process to the time of completion of the turnaround time of completion of the execution is called turnaround time. It is a time interval from submission of process to the execution completion of execution of the process, we call it as turnaround time. And turnaround time is the sum of the period spent in waiting to get into the memory and waiting in a ready queue and executing in CPU and doing some IO operation. All together we call it as turnaround time. It is a sum of waiting waiting for the memory. Okay, sum of the time duration it is waited for the memory and waiting inside the memory. Okay, that is nothing but waiting in the ready queue and executing on the CPU and executing the IO burst. All together we call it as turnaround time. Okay, This is nothing but it is a interval from time of submission of the process to time of completion of completion of execution of the process is called turnaround time. Okay, next one is waiting time. Waiting time is nothing but the amount of time a process has been waiting in a ready queue is called waiting time. Like a CPU scheduling algorithm does not affect the amount of time during which the process executes or does the IO. Okay, it affects only the amount of time that process spends waiting in the ready queue. Okay, this is not waiting time is nothing but the amount of time the process has been waiting in the waiting queue is called waiting time. Okay, it is not the thing like the process executing in the CPU is not the waiting time. Only here we concentrate the amount of time the process is waiting in the ready queue, waiting for the process. We call it as waiting queue, waiting time. Okay, next one is response time. Response time is nothing but amount of time it takes from when a request was submitted until the first response is produced, not the output, is called response time. Amount of time it takes from when a request was submitted until the first response was produced. Okay, not the output, is called response time. Okay, it is the response time is a measure of the time from the submission of the request until the first response is produced. We call it as response time. It's a measure of time from submission of request until the first response is produced. Okay, and this measure is called as response time. It is the time it takes to start responding, not the time takes to output the response. Okay, here output is not included in the response time. This is the amount of time it takes from when the request was submitted until the first response was produced. Okay, this is the scheduling criteria: CPU utilization, throughput, turnaround time, waiting time, and response time.